You are welcome to SKPAS International College. Thank you for watching my videos. If you have not yet subscribed to this channel, kindly subscribe to the channel, like the video, and share to your colleagues in different schools. Alright, we are still on hybridization, and just like I've been telling you always, chemistry is simply chem is try. If you don't try yourself home, you will find it so difficult. But once you sit home and you practice whatever we are taught, then it becomes very simple. Chem is try. So keep trying. In today's presentation, we are going to discuss how some molecules are formed, and we'll be able to explain some concepts regarding sigma and pi bonds. We've studied in our previous video that anytime a molecule has an sp hybridization, then that molecule will be linear in shape. And when you pick a molecule where the type of hybridization in the molecule becomes sp2, that molecule is a trigonal planar. As well as when you pick a molecule which has hybridization, sp3 hybridization, that molecule will say automatically becomes a tetrahedral molecule, or it is tetrahedral in shape. We want to look at how some molecules are formed, and we'll get the concept of sigma and pi bonds through these molecules. So let's take a typical example. We want to form ethene. Ethene belongs to this hydrocarbon having a double bond. So with all alkenes, they have a general formula which goes like this: CnH2n. Okay, so this is an alkene. When you do organic chemistry, we'll throw more light on that. So if it is having a carbon 2, ethene is having carbon 2. So C2H 2 times 2 give us 4. So we are going to work on this molecule C2H4. We want to know how this molecule is formed. Alright. Having said that, in my previous videos, we have been able to look at how these molecules are formed from their central atom. So anytime you want to determine the type of hybridization in a particular molecule, you first of all have to look at the central atom, and you write its configuration and follow the general rules. But with this, we want to examine how these molecules are formed and the type of hybridization in there. So let's first of all concentrate on the central atom. Our central atom happens to be carbon. We said that when you say central atom, it is the most electropositive element on the periodic table. So these elements, when you compare them, the carbon becomes our central atom. So we have to consider the electronic configuration of this carbon with atomic number 6. If you write the configuration, it's going to be 1s2, 2s2, and then 2p2. This 2p, the p orbital, is a degenerate orbital with subdivisions. So we have px, py, and pz. Now, we have said several times that in hybridization or in chemical bonding, bonds are formed with the valence electrons only. We do not use core electrons in the bond formation. So with this example, if you check from here, the outermost electron happens to be 2s2, 2p2. Alright, so if you are confused with that, you can use the core concept, which is 2:4. You get the 4 clearly. When you write the core electronic configuration, you use 2:4. So the outermost electron happens to be 4. So when you're able to write this configuration correctly, this happens to be the ground state electronic configuration. So we want to write it in a different way. Now, what will ask us, or what will enable us to write this in a different way? We want to understand why we need to write this in a different way. Now, when you pick the 2s, we said we use only valence electrons. So we are going to concentrate on these valence electrons. So we have 2 electrons filled here with 2 electrons in the p orbital. So this is px and this is py. And this becomes our pz. Now, in chemical bonding, we have said this several times that 2 electrons are not used in chemical bonding. It is only one. This will be having one, and we prefer to also bond with someone having one to form a bond. So if you see this 2s orbital, it has 2 electrons already. So for this to undergo chemical bonding, these 2 electrons, this one must donate 1 electron to the higher energy level. So we will have to promote this electron from this energy level to this energy level. The reason why we are promoting this electron, this 2s will prefer to undergo bonding. So it cannot use 2 electrons. When you have 2 electrons, you cannot undergo chemical bonding. In that case, this 2s becomes 2s2 becomes 2s1. So we will have only 1 electron left in this. And that 1 electron is not thrown away, but rather it is promoted to the other shell which is having no electron. So these 2 are already there. So this electron has been promoted to this has been promoted to this orbital. So in this case, we now have our px, py, then the pz. The question is, if you look at this diagram now, they are not all having 1 electron each. So 2s is having 1, 2ps 1, 2py 1, and then 2pz 1. Okay. Now, the question is, this carbon is bonded to another element having atomicity of 4. If you look at the covalency of that, it is 4. So this hydrogen must get this carbon must get 4 hybrid orbitals in order to be bonded with this hybrid. And let's take note of this. From this concept, you can see clearly that the carbons are 2. We have 2 atoms of the carbon. So it means you are going to repeat the carbon. In this case, let's have a view of the diagram, how it looks like. So for us to form this, it means we have to mix these 2s with all these in that order. But in doing this, look at this. Carbon is 2 bonded with 4 of the hydrogens. So let's pick the first one. This is my carbon. Now this carbon, before you can do that, you need to ask yourself, this is how it looks like. This is C2H4, so this is exactly how it looks like. It looks like this. At normal circumstances, this C2H4 has 1 sigma bond and 1 pi bond. And from here, it will give you a clue. Anytime we have a double bond in between this carbon formation, you should know the type of hybridization we are dealing with. We are going to deal with an sp2 hybridization for double bonds. So with this, it means we cannot mix all these. So what we are going to do is, we are only going to mix an S with 2 of the P's. So we are going to mix this 1, 2, 3. But remember, this is ready to be, this electron is ever ready to undergo the bonding. But because of the type of hybridization existing in this CHA2, it cannot mix all these. It can only mix 2 of these. So from here, this carbon is going to form 3 hybrid orbitals like this. Let's take note of this. Very, very important. Okay. So this is one going this way direction. This is another going this direction. So this carbon has managed to form these 3 hybrid orbitals. That is, when you mix this S and these 2 PS and PY, it forms 3 hybrid orbitals. That is for 1 carbon. Now, whatever you have done for 1 carbon, it is just a repetition of the other carbon. So it means there is another carbon here, and this carbon, let me bring it closer. There's another carbon here. This carbon is also bonded to this. This carbon is also bonded to this carbon. There are 2 of them. So it's also going to have the same thing this one was having. This first carbon was having. So this is also going to have 3 hybrid orbitals like this. So this is what you form. Now, after forming this, you realize that there has been one unhybridized orbital, which is the PZ. And from the locations, we gave the directions the other day in our previous video. That p orbital is dumbbell shape. So this becomes our x, which is px. Then there's y here. So this becomes our py. And the one on the ordinates based on mathematics becomes our what? Our z orbital. So this is px, py, and pz. So with this last one, pz, it means that since it is unhybridized, it must also appear in the bonding to show that I'm present. So we are going to represent this pz, the shape of this over there. And this pz, it looks like this. This is unhybridized. Okay, this is unhybridized, like this. And the same thing happens in this direction too, like this. It's unhybridized. The same thing happens like this. So you can see clearly that with this one, this bond form, the head-on overlap of this atomic orbital formed here is a sigma bond. And from this one, let me shade this portion so that it is clearly seen. With this one, should be a straight one like this. So with this one, you can see clearly that the shaded portion is the unhybridized orbital, which is the PZ. And this will also form a lateral line like this. So this is what we call the pi bond. So this is a pi bond and this is a sigma bond. So when we want to view it pictorial, the pictorial view of this upwards like this, it has formed one pi bond with one sigma bond. When we want to look at the pictorial view at the downwards direction, it has formed one sigma bond, one pi bond. Don't view the whole diagram and say it is having 2 pi bonds with one sigma bond. No. If you view the pictorial view in this direction, the upward direction, it has 1 pi bond, 1 sigma bond. If you view it in the lower pictorial, it has 1 sigma bond, 1 pi bond. And this is how it looks like. 1 sigma bond, 1 pi bond. Now the question is, this is bonded with 4 hydrogens, and hydrogen on the periodic table falls in the s block or the s orbital. So the hydrogen, we know it's spherical in shape. The s block is spherical in shape. So we have, these are the observable hydrogens. They are bonded. You can see it clearly now. So this is hydrogen, this is another hydrogen, this is hydrogen, and this is another hydrogen. So you can see they are all forming covalent bonds. This will bring 1 electron, and this will also bring 1. Then they share to form a covalent bond. This hydrogen will donate 1, and the carbon also donates 1 from its hybrid orbital. They share, they form a covalent bond. This will bring 1. This will also donate 1. They share and they form a covalent bond. This donates 1. This donates 1. They share and they form a covalent bond. So from this diagram, it is clearly seen that this is what we are really looking at. This is what we are really formed in a simplified way. And this is the view, the shape of this ethene. This is the actual shape. And this is what we have simplified this in this diagram. So this has 1 sigma bond and 1 pi bond. And this is how sigma bonds and pi bonds are formed. We said in our previous video that sigma bonds are formed as a result of what? The head-on. So this is the head-on overlap of atomic orbitals. It could be the SS orbital, the SP, or the PP. So this is formed. This is a sigma bond. We said that for the pi bonds, they are formed as a result of the lateral or the sideway. So this is the sideway, this sideway overlap of this p orbital. So you can see that this is a p orbital. It's not an s orbital. So this is a p orbital. So this is basically the concept behind how this ethene is having a double bond. So it's an sp2 hybridization. This is how ethene is formed. Thank you for watching this video. Like the video, share and comment. In my next video, I'll come out with how ethane is also formed, and we will be talking a lot about what we call the differences between diamond and graphite. Stay tuned and see you in my next video.